Hello everyone. Today we will talk about the three questions in assignment 2. Now look at the question 1. In question 1, we will be discussing how to construct confidence intervals for nonlinear functions of parameters. We will use asymptotic limit results and the delta method in our derivations. Now look at part A. In part A, we have a random sample drawn from the normal distribution, and the unknown parameter here is mu, and our target parameter is theta. A very natural estimator for theta is obtained by replacing mu with the sample mean x bar. That is, we propose the estimator is equal to E x bar minus 1. Since the sample mean is an unbiased estimator for mu, this transformation is intuitive given that E mu minus 1 is a continuous and monotopic function of mu. Now, let's leverage some limit results. Note that because x follows a normal distribution, so the sample mean x bar follows such a normal distribution. Since we are interested in theta, we apply the delta method with the transformation function. G mu is equal to E mu minus 1, and its derivative is like this. The delta method tells us such an equation. So we can know that the standard error for EX bar is this one. Hence, this one is approximately a normal distribution with estimated standard error of this. So we can construct the confidence interval. Because we know the z, and since we have a two-tailed interval with 4% total in details, in other words, our interval for mu can be written as this. And this is our result. Now look at part B. In part B, we have a random sample from a normal distribution. In this case, this mean is known to be 10, and the unknown parameter is sigma squared. The target parameter, however, is theta. Theta is equal to ln sigma. So a natural estimator for sigma is the sample standard derivation, which can be written as this. Then we estimate theta by taking the natural log of it. Now we want to construct a confidence interval for theta. We first need the asymptotic distribution of ln sigma. Now, applying the delta method with the transformation h of ln sigma, we calculate its derivation like this. Thus, by the delta method, we have this one. So, this tells us the asymptotic standard error for ln sigma is this one. Now, we can use the same way as part A to find our confidence interval. The result is this. It's very clearly okay. Let's move to the question 2. In question 2, we will solve a problem involving maximum likelihood estimation. And in our setting, we start with a random sample from a normal distribution, and we then define a new variable based on whether each observation is positive or non-positive. We will walk through it into two parts. Now look at part A. In part A, since x follows a normal distribution, the probability that any one observation is positive can be written as follows. And for a normal random variable, we have this one. But recall the symmetry of the normal distribution. 1 minus phi negative mu is equal to phi mu. Thus, we have set is equal to phi mu. This tells us the probability of a positive observation is a function of mu. However, in part A, we treat theta as the parameter to estimate. And then we will construct the likelihood function. Since for a given I, the probability mass function of yi is like this, and assuming the yi are independent, the likelihood function gives a sample of yi to yn like this one, where n is the number of observation and n1 is the number of successful. And then we will use the data. We are told that there are 4 positive observations and 6 non-positive observations. So we can substituting these values into the likelihood function, we get this one. And to find the MLE, we look for the value of theta that maximizes this likelihood. And a well-known result for the MLE of a probability parameter in a Bernoulli setting is that the MLE is the obverse proportion. Thus, we have this one. So the MLE for theta is 0.4. Now look at to part B. In part B, we need to estimate mu from theta. The first thing we need to do is relate theta to mu. Recall that earlier we established the relation theta is equal to phi mu, where phi is the cumulative distribution function of a standard normal distribution. And then we invert the relationship. Now that we have the MLE theta is equal to 0.4, we can estimate mu by inverting this relationship. And using the standard normal distribution table, we can find the result is like this. Now, let's look at the question 3. I think it's a little long, but it's not very difficult. Such as part A, we just need to calculate the mean and the variance of x. Let's consider a random variable x that takes the values 1 and 2 with probabilities given by this, where theta is a parameter in the interval 0 to 1. We can find the mean. The expected value Ex is calculated by summing the product of each value with its probability, rated as this one. And the variance is obtained from this equation. We just need to input the operation and we can get the result. For part B, we want to prove that the estimator converges in probability to theta. Okay, we look at this estimator. And we can find that the sample is independent and identically distribution. So we can use the weak law of large numbers. It tells us this thing. And now define the function gx like this. Notice that g is continuous at x, this point. And by the continuous mapping theorem, if xn bar converges in probability to mu, we can know that g xn bar also converges in probability to g mu. And here mu is equal to 2 over 2 minus theta. So that we can get this thing. Therefore, we conclude that our estimator converges in probability to theta. Now look at part C. It's a little long. but I think it's a little same with the question 1 and the question 2. Now we want to construct an approximated 95% confidence interval, and we know the observed data. The first thing we need to do is to calculate the sample mean and the variance of x, and it's very easy. And then recall that we know the estimator of set n is equal to gx bar, where gx is at that point. And we know the derivative of gx is like this. So we can get the asymptotic variance of xn bar. And applying the delta method, we have this one. So simplify the asymptotic variance, we can get the variance of set n is like this. And the next we need to do is just plug in the estimate. Since the true theta is unknown, we use our estimator, set n. Then we can get the variance of set n is like this, and the standard error is this. Then we can construct our confidence interval just like question 1 and question 2. It's like this. Okay. And in part A, we want to reflect our findings. First, our result interval is like this one. This one. Yes. And what about our theta? Yes, our theta lies within interval 0 to 1. So our result fits nicely within this range. But think about the values of the interval. The interval is rather wide and our sample is very little. So this can be attributed to the small sample size. With more data, the variance would decrease and the confidence interval would become narrow, and it can reflect greater precision in our estimate. And that is also what we want to do in statistics. Okay, that's all. Thank you for listening.